right? They're not too crazy. And yeah, I mean, like I said, I haven't largely haven't changed how I've made the tests for this class. For other class, I definitely have, right? For Math 133, like I said. Okay. So let's see. Now it occurs to me, I said last time we were going to talk about like chain rule and the inverse function theorem. We are still going to talk about those things, but then I realized I haven't done the derivative of sine and cosine yet. So we kind of have to do that first. So what we're going to do is we're going to start off with a little proposition. And that proposition is just a quick, straightforward limit. So the limit as, oh yeah, okay, we'll call it x. X approaches 0 of sine x over x is equal to 1. And the limit as x approaches 0 of 1 minus cos x over x is equal to 0. Okay, so we have to do these limits. It's basically going to be a squeeze theorem sort of argument. And you might say, well, why didn't we do this in the limit section? And the answer is, well, we could have, but there is a reason that we want to do it in the derivative section. And if you, well, you know, maybe I'll point it out. Try and think about like what these limits look like and see if you can figure out how they're related to derivatives. And actually, in that case, though, maybe I should write this as, it doesn't matter, right? But if I write the cosine as cos x minus 1, it might be more obvious. But we're claiming that it equals 0 anyway, right? So it doesn't matter whether I write 1 minus cos x or cos x minus 1. It introduces a minus sign. It's going to be 0 anyway. I'm going to write it as cos x minus 1 here just to maybe help you guess how the derivative is involved. And the proof of this, so we're going to do sine x first, and then we'll do cos x using the properties of how cos x is related to sine x. So for the proof of the first one, so let's do the first one. So the limit as x approaches 0, sine x over x. Okay, so to do this, it's just geometry, right? And we can't avoid geometry. We would like to eventually kind of not have to draw pictures to do stuff. But before we can do that, we need to like build up enough tools, right? So let me draw, let's see, I need some colors here. Let's draw, okay, here's the unit circle, right? So 1, 1. I'm going to draw a, let's see if I can. Draw this triangle here. Oh, my drawing skills, so bad. Okay, there we go. And maybe we'll use red here. All right, so we know that this height here, this is sine x, right? That's this height. And we know that this is cos x, right? Like that. Does anyone know this height right here? So if you, or I guess I should label x, right? So I'm going to say this angle here is x. Does anyone know the length of this far, like if you take the big triangle, so its base is 1, what is the height of this triangle? I think this is probably something that don't teach you in high school. I could be wrong though. No? This is tan. Okay, so the length of that rectangle, maybe let me, or not rectangle, triangle, the height of this triangle, that's tan x, right? So instead of stopping at where you hit the unit circle, what you do is you keep going such that your triangle has base 1, right? So right where the circle actually, the circle of radius 1 hits the x-axis, and you draw that triangle and it has a thing, right? Height over 1, not necessarily. I would say, so this is the geometric definition of tan, right? The fact that tan is equal to sine over cosine, which is something that we know is algebraically true, requires a little bit of work. But this is just the definition of tangent, right? So if you use like the circle to define what sine and cosine should be, the circle and the triangles that are involved, then, I mean, I guess you could think of it like that, Yonje, if you want to, but this is just the definition of tan, right? So I think in high school, they often tell you that tan is sine over cosine, and that's the definition of tan. It's not. That ends up being a property. This is the definition of tan. Okay. And, okay, I'm going to try and draw sine on its side, which luckily I can just turn my tablet because there's no way I was going to be able to draw sideways, because I actually need to draw in one more thing here. What color am I going to do? I guess I could do green. So I'm going to take it from this point and I'm going to go down here to one like this. Okay. And now we need to start labeling things. I'm going to call the origin O. That's a good point. O, P. Let's maybe call this Q, and let's call this R. Something like this. Okay, so this is already, you're just like, oh man, there's so much going on here. So just by inspection, note that we're going to have triangle OPQ is going to live inside of the sector. How do I draw a sector? Maybe like, no, that looks like a triangle. That looks like an eye, but whatever. OPQ lives inside triangle ORQ. Does everyone agree? Right, just based on the picture, no matter what X is, whatever that angle X is, this triangle OPQ lives inside of the sector OPQ, which itself lives inside of the big triangle ORQ. Does everyone agree? Does that make sense? Someone yell if that's okay. Okay, and so let's compute the areas of these things. Okay, so the area of triangle OPQ is what? So it's 1/2 base times height. The base is 1 and the height is sine, right? So we're going to get 1/2 sine x. Okay, now the sector, does anyone remember the equation for the area of a sector? Maybe we can just write this on the side here. So the area of a sector, what would we say? Subtended by theta? So yeah, I'll draw the sector for you. Okay, so the sector is the part of the unit circle that falls under this radius, right? So that's the sector. Do you see it? Yeah, exactly. It's the slice of pizza. X over 2 r squared, right? Exactly. So like I've said here, theta, so it'd be theta r squared over 2. And if you don't remember that formula, it's relatively easy just to derive on the fly. How do you do it? Like, where does this formula come from? Does anyone remember? Right, the ratio of x and 2 pi and multiplied by the area of the circle, right? So how would you figure out? Yeah, exactly. So what you do is you take the area of the whole circle, pi r squared, right? We know that. And then what you do is you say, okay, well, listen, I have this angle x written in radians here, right? I have this angle x, and I know that there are 2 pi radians in the whole circle. So if I want to figure out how much of the circle I've cut out, what I'm going to do is I'm going to figure out, well, how many radians of the 2 pi radians have I done, right? So you can see if theta is 2 pi, i.e. I did the entire circle, then theta over 2 pi is just 1. If theta is just pi, then I'm going to get half the circle and so on and so forth, right? So this theta over 2 pi thing is just keeping track of how much of the circle did you actually sweep out. And if you simplify this, this is what you get, right? Theta r squared over 2. In our case, r is just 1, right? We're talking about the unit circle. As Divyansh pointed out, we're using x instead of theta. So this should just give us 1/2 x. Right, like that. And then triangle ORQ, well, again, it's 1/2 base times height. This time I am going to write it as sine and cosine. So the actual answer is 1/2 tan x, right? But let me write it as sine over cosine, like that. Okay, so I get this inequality of functions as functions of x, which is really, really nice. Now you might say, okay, I don't quite see sine x over x here. And you're right, we're going to get it in a second, but is everyone okay with this collection of inequalities? Right, which I think is nice because it's a statement about functions and we use some geometry in order to be able to figure it out. Okay, so what I'm going to do is I'm going to divide everything by 1/2 sine x. Okay, so divide by 1/2 sine x. So in this case, you can see I've actually, so cos x is the base. What do you, for which one? For the ORQ? For ORQ, the base is 1, right? Cos x actually isn't needed here, right? We never actually use cos, but for triangle ORQ, that's the base, right? So its base is 1. So it's 1/2 times 1 times the height, and the height in this case is tan, right? That's why we got 1/2 tan x. Okay, so hopefully that makes sense. Now, if x is greater than 0, or let's say x is between 0 and 2 pi, x in 0, no, let's just do pi over 2 so that this number is positive. Then we're going to get 1 is less than or equal to x over sine x is less than or equal to 1 over cosine x, right? And the inequalities are preserved precisely because x is between 0 and pi over 2, so that guarantees that 1/2 sine x is actually non-negative, so the inequalities are preserved. And then if we take the reciprocal, so it's actually just going to flip the inequalities. So we're going to get cos x is less than or equal to sine x over x is less than or equal to 1, right? And now we're done because by the squeeze theorem, as we let x go to 0, we know that cos x is going to go to 1, right? We said cos is continuous. So as x goes to 0, cos goes to 1. The constant function 1 definitely goes to 1. So the squeeze theorem tells us that sine x over x becomes 1. All right, so by the squeeze theorem, I guess I should technically say the limit as x goes to 0 from the right, sine x over x is equal to 1. Okay. Now, if you do x between negative pi over 2 and 0, you draw the same sort of picture and the inequalities still effectively all work out. You just have to be a little bit careful about the sign of sine, which is a weird thing to say, but the sign of sine, right? So in this case, what I will just say is a similar argument holds when x is in negative pi by 2 to 0, right? So i.e. we would draw the same sort of picture, but we would draw the picture beneath the x-axis instead of above the x-axis, right, in that lower right-hand quadrant. And you can imagine when you draw it, you're going to get the exact same sort of inequality of functions. But at the end of the day, it doesn't matter. So you're going to divide by 1/2 sine x, right? So this relationship should still be true, even if you draw it beneath the x-axis. When you divide by 1/2 sine x, though, I guess I should take x to be an open 0, right? Because we don't want to divide by 0. This time, though, when you divide by 1/2 sine x, you're going to divide by a negative number. So your inequalities are going to flip. Then you reciprocal, so it flips back. And what you're going to get is that this double star relationship is true, except all the less than or equal to signs are flipped with greater than or equal to signs. But you don't care because the squeeze theorem is still true, right? So basically, when you redraw this picture and you do it for x in negative pi by 2 to 0, double star here is going to be exactly the same, except all, or maybe I should make, well, maybe let's call it triple star. Triple star will be exactly the same, except all the inequalities will be flipped. but that doesn't matter because Squeeze theorem still applies, right? Instead of bounding sine x over x between cosine 1, you're going to, well, no, yeah, obviously the inequalities must still hold, right? I haven't worked it out in a while. Either way, just go through the argument and you'll see that it still works out. You get exactly the same relationship, but you do kind of have to treat them as separate things, okay? So try it, and if you have any issues, bring it up with me, because I recall doing it and I don't recall getting any issues. So a similar argument holds when x is between negative pi by 2 and 0. And so that gives us that the total limit, not just the one-sided limit, is equal to 1. Okay? So like I said, if you want, just give it a try. And then if you do run into issues, let me know and I'll come in and try and fix it. But there shouldn't be any issues. It wasn't too difficult. And then just like we did when we were doing continuity, instead of redoing a geometric proof for cosine, let's just use the fact that we know how sine and cosine are related, right? So for, okay, I am actually going to do, no, let's be consistent. I'll do cos x minus 1. So what I'm going to do is I'm going to multiply by the conjugate, right? So I'm going to multiply top and bottom by cos x plus 1. So I'm going to do cos x. And you'll see why normally you actually write it the other way. You normally write it as 1 minus cos x instead of cos x minus 1. And the reason is that when you do this, you get cos squared x minus 1 divided by x times cos x plus 1. Cos squared minus 1 is negative sine squared. Right? And so that's why we would normally do 1 minus cos x, so that if you're doing the limit of 1 minus cos x, instead of getting negative sine squared, you get positive sine squared, but whatever, it doesn't matter. We're going to show it's equal to 0. And we can write this as the following, because all of these limits exist. So what do I want to do? I want to do sine x over x times the limit as x approaches 0, sine x all over 1 plus cos x. Right? So here I've used the limit laws, but I've used the fact that 1, sine x over x exists because I just proved that it existed. 2, sine x over 1 plus cos x is continuous, right? We know that sine and cos are both everywhere continuous. The denominator here, 1 plus cos x, is not 0, at 0. So that whole function is continuous, so I know that its limit exists. And now when I evaluate each of these, what am I going to get? I'm going to get negative 1 times 0 over 1, and that gives me 0. Right? Maybe I could write that even more suggestively, 1 plus 0. It doesn't matter. You get 0 from that. Okay? And so we're done. So now we've given these limits, and we've proven that they exist. And it's, not obvious, right? It took a bit of work. So are there any questions about this? Okay, does anyone recognize what are these limits in terms of derivatives? What are they? Nobody sees them? That the derivatives of sine and cosine at 0, right? So let me say note. So if you wanted to compute the derivative at 0 of sine x, what would that be? You would take the limit as x approaches 0 of sine x minus sine 0 divided by x minus 0. But sine of 0 is 0, right? And so between sine and cosine, okay, sure. Yeah, do you want me to rewrite that down? This is just, right, this is the Pythagorean identity, right? Sine squared x. Like, there's only 2 identities that I think are worth remembering in this class. So one is the Pythagorean identity, right? Sine squared plus cos squared equals 1. That one's important. And then the other one is probably the angle sum identity. So sine x plus y, sine x cos y plus cos x sine y. Okay, those are the only two. If you remember those two identities, almost everything else comes from that, right? Yeah, so Kevin, we know that that one exists. This is a good question. This function here, this is continuous, right? So we proved previously that sine and cos are continuous everywhere, but in particular, they're continuous at 0. And so if you take two continuous functions and you take their quotient, then their quotient is continuous as long as the denominator is not 0, right? At the point that you're limiting at. And since 1 plus cos x is equal to 1, the denominator is not 0. So that whole function there is continuous because its denominator is not 0. So I know that its limit exists, and I can evaluate its limit just by plugging x equals 0 in. Yeah. Okay. So does everyone see that this is, and yes, yeah, Yoanji, we proved that cos x was continuous, and that, right, cos of 0 is 1. So yeah, the limit as x approaches 0 if cosine x is equal to 1. Yeah. Okay, so does everyone see this? So what we actually just proved is that the derivative of sine at 0 is equal to 1, right? Sure, where? Oh, yeah, sorry, yeah, it should be 1 plus 1, right. Yeah, you're right, thank you. Okay, and you can imagine same sort of thing for cosine x. So for cos x, you would do exactly the same thing. And you imagine, yeah, you're going to get the other limit, right? So this gives you cos x minus cos 0 divided by x minus 0. That's the limit as x approaches 0 of cos x minus 1 over x. And we just showed that that was equal to 0, right? So this is what I'm saying, why it makes sense to talk about these limits now when we're talking about derivatives, because what we actually just showed is that sine and cos are both differentiable at 0, and we found the values of their derivatives. Now, if you remember, when we were talking about continuity of sine and cosine, when we wanted to prove that sine was continuous everywhere, we proved that it was continuous at 0, and then we extended it to every other point using the angle sum identity, right? So using number 2 up here. So using the angle sum identity, we could take continuity at 0 and spread it to every other point. And we're going to do the exact same thing with differentiability. We know that the function is differentiable at 0. We're going to use that identity in order to show that sine is actually differentiable everywhere, right? So that leads us to a nice little theorem. And that theorem is that sine, the functions sine x and cosine x are differentiable everywhere. On R, and the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, which is really, really nice. And in fact, the fact that sine and cosine have this nice relationship between them is crazy important, right? It ends up coming up all the time in sorts of like differential equations. There will be even crazier things that sort of manifest because of this later. Okay, so I'll do the proof only for sine. The proof for cosine is almost identical, though for the proof of cosine, you have to use the cosine angle sum identity, which, you know, you can look up. But yeah, so let's do it for sine. But it's almost identical. Okay, so again, we want to show it's differentiable. So what we're going to do is we're just going to check, right? If I compute the derivative at a point C, what is that? So that's going to be the limit. And again, this time I actually want to use the h goes to 0 definition. Actually, I guess we could just do x. Okay, and this time again, it's really critical that I'm using this definition precisely because I have, is it going to show up? Right at the top left of that screen there, I have that identity, right? Sine of x plus y. So I really want sine of x plus h to show up so that I can use that identity. Okay, so I'm going to invoke that identity now. So I'm going to get sine x cos h plus sine h cos x minus sine x all divided by h. Okay, and now what I can do is I can factor out a sine x. And again, I'm just going to immediately use the limit laws. And then we'll just check after to make sure that it was okay because all of the limits existed. So I'm going to get cos h minus 1 over h plus cos x times the limit as h goes to 0 sine h over h, like that, right? And we sanity check ourselves. So I've used the limit laws, but we have to double check, was I allowed to do this? Oh yes, okay, I know that all of these limits exist. And don't forget, I can pull out the sine x and the cos x because the limit is in terms of h, right? Sine x and cos x are just constants with respect to this limit. And lo and behold, these are exactly the derivative of sine and the derivatives of cosine at 0, which we just found, right? So we know that this first thing, this is equal to 0. And we know that this thing is equal to 1. So at the end of it all, I get cos x. That's defined for every real number. And so the function is differentiable and the derivative of sine is cosine, right? And we're done. And so again, the proof for cosine x is you would do exactly the same thing, but instead of using the double sum or the angle sum identity for sine, you would use it for cosine. And again, just look it up if you don't remember what it is. And exactly the same sort of thing. Once you factor out the sine x and the cosine x out, you're going to be left with these two limits. And these are precisely the two limits that we just found. And yeah, I mean, one of them is 0, one of them is 1. And what you're going to find is that negative sine x pops out. Okay. And the reason for the negative sign is that cos x plus y has a minus sign in it, right? It's kind of weird. It's not like sine in that sense. Cos x plus y is cos x cos y minus sine x sine y, if I recall correctly. And so that minus sign is that it comes from the angle sum identity, right? That's why the minus sign there shows up. Okay. Everyone happy? Does that make sense? Okay, cool. So we know the derivative of sine is cosine and cosine is negative sine. In fact, there's something interesting here. It's not, is there an obvious thing that I can say here? I guess not, but basically let me put it this. Do you all know, you've all probably heard about it, even if you haven't studied it in any great detail. You've all heard of this number here, right? The imaginary number, I is equal to -1. Or square root of -1, right? Exactly, yeah, complex number. And what you probably know is that I squared is -1, I cubed is -I, and I to the 4 is equal to 1, right? And then the pattern repeats. So I to the 5, we could just say I is equal to I here or something. So I to the 5 is equal to I to the 6 is -1, I to the 7 is I to the 8 is 1, right? So it has this fourfold periodicity, right? It goes through I, -1, I, and then back to 1. And it's the same sort of thing. We have something interesting happen here, where if I compute the derivative of sine x, I get, well, let me say it. So let's say I take the 0th derivative of sine x, namely I don't take any derivatives. So I get sine x. If I take one derivative of sine x, I get cos x. if I take 2 derivatives of sine x, I get negative sine x. And if I take 3 derivatives of sine x, I get negative cosine x. And then it repeats, right? So again, notice that we have exactly the same sort of pattern as what's happening with I, where it takes us 4 derivatives to get back to sine. And in between there, we just jump between sine, cosine, negative sine, and negative cosine. And that's exactly what we did with the imaginary number I, right? We would jump between I, negative 1, negative I, and 1. And this is not a coincidence. There is an imaginary number in here. Okay, so there is an imaginary number hiding inside of sine and cosine, which is precisely responsible for this fourfold periodicity, right? It is 100% the fact that we get this. Yeah, no, it's not the I in sine. I like it though. But yeah, there is secretly an I hiding in the definition of sine and cosine, which is precisely the reason why we get this fourfold periodicity. Okay, so it's super cool. I think it's a really interesting thing. We might be able to talk about it a little bit more by the end of the year, like in March and April sort of thing. But yeah, if you remind me, I'll try and bring this up. There is secretly a complex number hidden inside of sine and cosine that is responsible for this. Okay, so I think that that's a nice, cool thing. Just something kind of like keep on your radar. Okay, so the next thing, and of course, if you all want to now, you can, differentiate tan. Actually, we should probably do that because I will expect you to know this one for sure. So exercise. So let's say show that I'm going to give this function a name, tan x. I'm going to call it f, is differentiable on R without, what is it? So cosine can't be 0. So it's going to be like pi, 3 pi, or pi over 2, 3 pi over 2. So this is going to be the half odd multiple integers of pi. Right? And that its derivative is secant squared. Use sine over, and exactly, yeah, exactly, Yuanji, right? We're going to use, and the quotient rule, right? So we're going to write tan as sine over cos, and then we're going to use the quotient rule to figure it out. Okay, so solution. So let's do f prime of x. And again, to figure out where your function is differentiable, just compute the derivative and see where the derivative is actually defined, right? So that's going to be the derivative of sine over cos. Now, I don't like using this notation, but I am going to use it here. So the derivative of the top, so I'm going to write this as sine of x prime. I really don't like that notation, but it is appropriate here just because I don't want to let g of x be sine x and let h of x be cosine x. I just want to kind of let them be what they're called. So I am going to be a little bit sloppy in notation here, but I think we all know what I'm saying. Right? So by the quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top, all divided by the bottom squared. I know what the derivative of sine is. So I'm going to get cos squared x, right? Derivative of cosine is negative sine x. So the two minus signs cancel each other out. So I'm going to get plus sine squared x, right? And then sine squared plus cos squared is equal to 1. So this is going to be 1 over cos squared, and that's secant squared, right? And so this is going to exist anywhere that secant exists, and secant exists anywhere where cosine is not 0, right? And that's precisely the odd half integer multiples of pi, whatever weirdness that is, right? So this exists wherever cos x is not equal to 0, i.e. On exactly what I said, right? 2k plus 1 pi over 2, k and z. Right, and we're done. And of course, now you can do everything. I'm going to let you do the table yourself. You need to be able to finish it. But again, the entire course is online. So if you really want to, you can just go to Google and be like, table of trigonometric derivatives, right? And let's see if even I remember them. So derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. And then the derivative of cotangent is negative 1 over cosecant squared, I think. But the reality is that I don't remember. If I really need them on the fly, I'll either look them up or derive them from scratch, right? Like they're not that hard to find on your own. It's all either just product or quotient rules and, you know, and maybe a little bit of trigonometric identities, but not really. So it's relatively straightforward to just rederive these on the fly, right? It's definitely not worth memorizing that table ever. And again, like, especially if you do more mathematics, do you know, this is the only class in which I do trigonometry, really? Because, you know, in 133, we don't do any trig because apparently things don't oscillate in finance. And then in 257, you know, the math is so advanced that we very rarely deal with actual functions. So sine and cosine never come up. So it's funny because I always, when I skip teaching 157 in a year, right, because I didn't teach it last year, for example, I don't do any trigonometry for an entire year and have to remember all of my identities and they have to come back. But again, the point is they're not worth remembering. Just rederive them on the fly, right? And same thing, like I don't remember what the derivative of arc cosecant is, right? Off the top of my head. Like I don't remember what that is, but I know how to find it. And probably not by the end of today, but by the end of Thursday, I'll show you how to find it as well. And you'll be able to just do it if you need it, right? Just figure out what it is on the fly. Definitely not worth remembering. And in fact, that's what I say about these trigonometric identities. So these two here, right on the left-hand side, the Pythagorean and the angle sum identity for sine and probably for cosine, those are the only identities you need. If you know those two identities, you can basically find every other identity that you want. I know in high school, you know, for example, they spend a lot of time being like, oh, here I list all the, you know, trigonometric identities that you need to remember, but they all come from these two, right? Like, you know, one of them is what, 1 plus secant, or 1 plus tangent squared is secant squared. That's just, you take the Pythagorean identity and you divide everything by cosine, right? Or the one with cosecant is where you divide everything by sine, right? So you don't remember those identities. They're not worth remembering. Just take the Pythagorean identity and divide it by sine squared or cosine squared, right? Same thing, that like sine, right? What is it? There's a sine 2x is 2 sine x cos x. Well, that comes from the angle sum identity, right? Where you just let x be equal to y and then you plug them in. Yeah, I would remember, that one is worth remembering as well. That is where a bunch of them come up from. And I think you can get that identity from the sine x plus y one, but it's not straightforward. So I think the cos x plus y one is worth remembering as well. But again, they all basically come from those two. And if you remember the sine x plus y, the cos x plus y one is easy to remember because it's, again, just the coses occur together, the sines occur together, and there's a minus sign, right? So they're pretty similar. So once you remember one, you usually have the other one. Okay, so let's see. I wonder if I can do this before we go, before we take a break. Okay, so we're going to do another theorem. So this theorem is the chain rule. Okay, and the chain rule is how you differentiate the composition of two functions, right? So it states if g is differentiable at C and f is differentiable at g of C, then f compose g is differentiable at C and f composed g prime of c is f prime g of c g prime of c, like that. Okay. Now, the chain rule is one of these things that you want. The proof seems like it should be easier than it is. And in fact, I know I say that and you're kind of like, oh, there's no way this is an easy proof. But to an extent there is. There's a proof that works for like 99.999% of functions, right? Like almost any function you could write down, the following proof is going to work. So I'm going to show it to you. And then I'm going to be like, yeah, but this proof doesn't work for every single function, so it's not actually a proof. Okay, so here's our bad proof. And it's bad because it doesn't work for everything, but it works for almost everything. Okay, so here's the bad proof. And the proof is to just do this. So the limit, or it's just, again, what do we want to do? We're just going to compute the derivative, right? So we're going to say the derivative of f composed g at the point C is the limit as x approaches C like that, right? Because if we start with the good proof, you won't understand what I'm doing. Because the good proof is just a fix of the bad proof, but it's kind of like if you do it from scratch, you're just like, what the hell happened? So by seeing the bad proof first, you have an idea of why we're trying to fix it, right? And how exactly the fix works. Yeah, so I think it's worthwhile doing. Okay, so I haven't done anything here, right? I've literally just written out the definition. This is the definition of what the derivative of f composed g is. And what I want to do is I'm going to multiply and divide by something clever, in this case, g of x minus g of c. Okay, so let's just multiply and divide by that and write it out again in a clever way. Like so. Okay, so this thing right here, this is certainly as x approaches c, that's going to give you g prime of c, right? And this thing almost always, almost like, again, for almost any function you can think of, except for a few really, really pathological ones, not even product rule, right? Because we don't have to use the product rule here because these are limits, right? And in limits, you don't have to use the product rule. You just know the limit of the product is the product of the limits, right? You don't have to do anything tricky like this. Most of the time, this is in fact f prime g of c, right? So because let's think about what is the derivative of f at g of c, right? But do you see that this is going to be true? This is kind of the tricky part right here, seeing that this is f prime of g of c. But maybe as a little side thing, what should f prime g of c be? That should be the limit as x approaches g of c of f of x minus f of g of c. My pen just died. Okay. Right? And what you're going to say is, okay, well, look, those aren't the same thing, right? These limits aren't the same, but they should be after a change of variable, right? Remember, we have this theorem that tells us how to change a variable. So what I would like to do up here is do something like let y be equal to g of x. So as x approaches c, y approaches g of c. And then if I replace this limit everywhere I see a g of x with a y, then that is exactly that limit below, right? So what I want to do, yeah, so here, let me just, this is off to the side. So what we kind of want to do is set y to be g of x. So y approaches g of c as x approaches c, and then write this limit down. as the limit as y approaches g of c, f of y minus f of g of c divided by y minus g of c. And that should be equal to f prime g of c. Do you see how that's supposed to work? Like this is how I do it, right? I would use the limit law to break this limit into two limits, right? The limit of the first thing, the limit of the second thing. And then I would use a change of variable on the first part to write it like this. And then I would say that, yeah, this is just f prime g of c. Does everyone agree? Like that's how that would work if I was allowed to do all that, right? Is anyone confused? Right, how could this be wrong? So this is a great question. What's wrong with this proof? All right, so question. What's wrong? Oh, but we assumed that g is differentiable at c, right? That's one of our assumptions. So we do have that. And we also know that f is differentiable at g of c, right? We know that f is differentiable at g of c, so this limit also exists. So both of these limits exist, right? That's not the issue. So what's wrong? Okay, yes, yeah, it is possible that g of x minus g of c is equal to 0. Absolutely, that's a possibility. Yes, and in fact, that's related to the big issue. That is 100% the issue, Jackie, but it's kind of, it is buried deep within the, like there's another issue which has that built into it. So the issue, which Jackie has hit on, and Jackie, that is 100% the issue. The issue is that when I want to use change of variables, I can't just do this. I can't just say let y be equal to g of x, and now y approaches g of c as x approaches c, right? If you go back and you look at when we proved change of variables, there was a condition that needed to be true. Does anyone remember what it is? I might even be able to find it. When did we talk about this? Nope. Probably somewhere around here. Let's see. Oh yeah, here it is. Nope, that's the continuity. There it is. Here's the change of variables theorem, right? When we did it, this is the theorem that I want to use in order to be able to turn that f of g limit into just the derivative of f evaluated at c. And what you see here is one of these two things has to be true. Either f is continuous at the point, right? Either f is continuous at its limit point, or there exists a row such that g of x is not equal to L for all x, for all of, in a neighborhood of our limiting point, okay? Now, if we go back, let's remember, this was October 19th, so let's go back here. This function, okay, or let me write it out and say, so to apply the change of variables, we either need that one, f of g of x, or what do I want to say? That f of x minus f of g of c divided by x minus c is continuous at g of c, or two, g of x does not equal g of c for all x near c, right? One of these two things has to be true. Do you agree? Okay, now Jackie, you've hit exactly on a point, right? Where you said g of x minus g of c, is it possible that that's equal to 0? Yes, it is. And in fact, it's possible that is precisely the condition that g of x equals g of c, right? And we're saying that g of x needs to not be equal to g of c. So the reality is that this is going to be impossible to fix. This will never be, we can't guarantee that this will ever be true. Because there are functions that are differentiable at a point C, and g of x and like are equal to the value of their derivative infinitely often in an arbitrarily small neighborhood of their limiting point. Okay, so there are examples of functions which do satisfy property number, like that break property number 2 here. So we can't fix property number 2. Now, property number 1, is that function continuous at g of c? I'm sorry, this should actually be g of c here in the denominator. Right? No, f is, we have to be careful here. F is differentiable at c, and therefore f is continuous. But the question is this function continuous? Right? And no, this function isn't even defined at g of c. Right? Does everyone agree? Because if you plug g of c into this function, right, what does continuity means? I should be able to plug g of c in and get out the value of the limit, but I can't plug g of c into this equation or into this function because I would be dividing by, I would get 0 divided by 0, right? So this function isn't continuous. However, what type of discontinuity does this function have at g of c? It is removable. Exactly, right? Because we know this limit exists. Right? We know this limit exists precisely because, as Duanche said, this function is differentiable, right? So we know that this limit exists and its value is f prime g of c. So the answer is that we can't use this function, but we can fix it if we plug the hole, right? So we can't use the function above. But instead, what we're going to do is we're going to define this function. Right? This function is continuous. Right? And it's almost exactly equal to that function above. The only difference is what actually happens at the point x equals g of c, right? Okay, so what I'd like to do now, I think at this point it's easy to have been like, okay, well, what the heck are we going to do then? So what I'm going to do is right here at this part of the proof here, I'm going to replace this with the function capital F. Okay. And I'm going to argue that, first of all, that does not change the limit. And that second of all, now that this function is continuous, I am allowed to make this change of variable. Okay. So again, let's recap. The issue is I cannot do the change of variable on this function as it exists, right? Or rather, I should say this function is f of g of x, right? So I cannot apply the change of variable to that blue rectangle as it exists because it satisfies neither of the two properties that I need to apply the change of variable. I don't know that that function is continuous. In fact, I know that function is not continuous, and I don't know that g of x is not equal to g of c. What I can do, though, is create a new function called capital F. Argue that, look, these functions are basically the same. Now plug it into that equation, and now I can apply the change of variables. So it seems like silly. It seems silly because like F, capital F and that function in the blue rectangle are basically the same function, but they're not. They're not the same function. So for me to be rigorous, I do need to make this fix, right? Okay. And this is what I'm saying about like, this is why we do the bad proof first, so you can see the intuition, hopefully, behind why this is going to work, what exactly the issue is, and how we're going to fix it. Because the proof that we're about to do is, imagine if I just said, define this function, capital F, notice that it satisfies the things that we're about to do, therefore we're done. You'd be like, okay, sure, but why did I do that, right? So this function is continuous, right? And moreover, I claim that f of g of x minus f of g of c divided by x minus c for all x. Okay, so this is my claim. This is me, okay, if I go back up here at the top of the bad proof, right? You see where the blue rectangle box is at the top there? This is me saying, look, get rid of the limits for now. This thing here is equal to f of g of x times this thing, right? So those three blue boxes at the top are equal to the blue box at the bottom if I replace that function, which is badly behaved, with capital F of g of x, right? Okay, so that's what I'm saying. And then that way, when I apply the limit to the left-hand side, I can apply the limit to the right-hand side, and then I can use change of variables on the function capital F. Does everyone see how this is going to work? How this is the fix? Like, are there any? Because I wouldn't be surprised if you were confused here, because it is a little bit confusing. I know. Okay, sure. So let me label the boxes. Here's box 1, box 2, box 3. Box 2 is bad. Okay, we can't use box 2 because we can't apply change of variables to box 2, right? Box 2 is bad, right? We can't apply change of variables to box 2. So I want to replace box 2 so 1, this is the new 2, and this is the 3, okay? So what I want to do is replace box 2 with new box 2. Okay, and so what I'm showing here, what my claim is that, you know, ignore the limits. These are equal as functions, right? But it actually doesn't make any difference whether I use as functions without limits. It doesn't make any difference whether I use old box 2 or new box 2. These two things are equal as functions. Box 1 is equal to both old box 2 times old box 3 and new box 2 times new box 3. Does that make sense? So that's the claim. Could you go through what happens if x equals g of c? So I'm going to, as part of this claim, yeah. So I'm a bit confused about the choice of f prime g of c at x equals g of c. Okay, sure. So, I mean, that's just what we need for this function to be continuous, right? At g of c. Maybe let me say this. So this is continuous at g of c, right? And the reason is, and you know, some of you might not be able to do this because you can't just magically make your stuff go down, but so the limit as x approaches g of c of f of x. So again, we look at everything except g of c when we do that, right? Oops, sorry, g of c. Right? This is precisely the definition of what it means for f to be differentiable at g of c. Right? And so that's why we choose f prime g of c, right? This is the definition. If you look at this, this is the definition of what it means for f to be differentiable at the point g of c. And in order for big F to be continuous, that has to be equal to big F G of C, right? So that's why we choose little f prime G of C. So does that make sense, Mahmoud? Dude, is it? Right, I just wanted this function to be continuous. So that discontinuity is removable, so I just plug the value of the limit in at that point. Okay, not certain if it's all right or not. Like if the point G of C is bugging you, again, just for now, call G of C something else, right? Call G of C 7 and write out what it would mean for little f to be differentiable at 7. And you'll be like, oh yeah, okay, I would get exactly that definition. It's just everywhere there's a G of C, I would put a number 7, right? So don't be like thrown off by the fact that G of C keeps showing up here. It's just a number. And so when you plug it in to the definition of the derivative, just everywhere you would normally put in your number, you would put in G of C instead, right? Okay, so like to see that this claim is true, we actually have to break it into two cases. So case 1 is what happens if x is equal to G of C, right? Well, the left-hand side, we would get 0. And the right-hand side, we would get f. The right-hand side is f prime G of C times 0, which is also equal to 0, right? So both of these functions are equal when x is equal to G of C. Wait a second, hold on. I need to make sure that I did that correctly because that doesn't look quite right. So claim f of G of x when x, no, sorry, when G of x equals G of C. Right, there we go. Right, so the left-hand side, maybe we could expand this out. So the left-hand side becomes f, remember G of x is G of C, so I get f of G of C minus f of G of C. That's why this gives me 0. The right-hand side gives me f prime G of C times G of C minus G of C all over x minus c. That's also equal to 0, right? So they are equal when G of x is equal to G of C. And when they're not equal, well, then I have the right-hand side is f of G of x minus f of G of C divided by G of x minus G of C times G of x minus G of C divided by x minus c. The G of x minus G of c's cancel. And that is the left-hand side. Okay, so I've shown now in all possible two cases, because either G of x is equal to G of C or it's not. But in doing this, these two things are equal. So now I can take the limit. So thus, f composed G prime of C is the limit as x approaches C, f of G of x minus f of G of C divided by x minus c. That is, because both of these limits exist, approaches c, G of x minus G of C divided by x minus c equals f prime G of C, G prime of C, and that's what I wanted to show. Okay? All right. So this proof, okay, there it is in totality. This is a tough proof. And again, do you see what I mean by like that bad proof is one line, basically, right? Maybe it's 2 line if you want to include change of variables. It's a 2-line proof. And it works for, again, almost any theorem, almost any function that you could think of. But I can construct pathological functions for which are differentiable and their composition is differentiable, but this proof does not work. So there's a small hole in our proof and we have to patch that hole. Unfortunately, the patch ends up being quite big because even though it turns out the hole is small, the fix to that hole ends up being a little bit technical. This is why I show you the bad proof first. The bad proof, like I said, works almost all the time. And it's where your intuition for the chain rule should come from. Okay, you should have an intuition based off of the bad proof at the beginning. But this is 157. I have to show you the proper proof. The proper proof is much scarier, but it's, like I said, it's technical just to fix this small, stupid fact and ends up, significantly complicating the proof just for the sake of a handful of functions that misbehave in this way, right? So that's how you have to fix this. If we want to use change of variables, we have to make sure that the function is continuous. So we have to replace old box 2 by new box 2, which is a continuous function. For case 2, y is the right-hand side equal to, okay, sure. So this is f of g of x, right? Because look at the definition of f of x. Okay, I'll try and keep them both up at the same time here. I maybe should have used different colors so you know which boxes you're looking at. So look at this, right? Because we're in the case where g of x does not equal g of c. And then look at this. So if you took that top thing, exactly, yeah, right? Because we're doing the composition f of g of x, right? Right? So everywhere that we've got an x, we're going to put a g of x instead, right? Because same thing here. In the original claim, we've got a g of x in it. Yeah. Okay, anyone else? That's good. Again, you might need to think about this one for a bit. This is one of these nasty questions. Legitimately, I luckily was never asked this, though I would have been very happy to. I know one of my good friends, Chris Eagle, who is a professor at the University of Victoria. So when he was at UVic and he was giving his job talk for getting hired there, they asked him, right? Because he was a teaching prof as well. So they were like, okay, well, listen, smart guy, tell us, in the proof of the chain rule, or they said, hey, prove the chain rule for us. And what they were expecting him to do is just to write down the simple proof. And he was like, okay, listen, there is actually this nasty caveat about this, and here it is. And he had to justify to the committee why, if you're basically not teaching 157, it's stupid to do the full proof, right? And that if you were doing this in something like 137, or even if you were doing it in 135 for whatever reason, why you basically just give the bad proof. So you have the full good proof precisely because you are in the super fancy 157 class. Otherwise, many classes would just kind of give you the bad proof, but the bad proof is technically wrong, right? It's a bad proof. It is not the real proof. Okay, so this has actually come up in job talks for some of my colleagues, believe it or not. All right, so again, I think you're gonna have to stare at this for a bit and convince yourself what the issue is, and the fact that this is the fix, that is tricky. Okay, I really don't expect you to have gotten this on your first read through. If you did, phenomenal, that's great. If not, think about it a little bit more. And on your own, even try and redo the proof yourself and convince yourself where the issue occurs, right? And it really is this fact that you cannot guarantee when you multiply and divide by g of x minus g of c, you can't guarantee that thing's never zero, right? And if that thing's never zero, then you're always leaving your epsilon band because your function just isn't defined in a neighborhood. Remember, for your limit to be defined, you need to be defined everywhere in a neighborhood of your point. But if g of x minus g of c is always zero in some small open interval of your limiting point, you just can't take a limit. You're not allowed, right? You don't satisfy one of the definitions of a limit. This is a very technical fix, right? And I know it's probably seems stupid. It's very technical. We've got to do it anyway. Okay, so that ended up taking a little bit longer than I had anticipated, but that's okay. I don't mind spending some more time on it, as long as everyone hopefully has a better understanding of it. On the other hand, though, it did kind of push us a little bit later into our break than I had anticipated. Let's take it now. I have 10:23 by my watch, so we'll take 10 minutes. We'll come back at 10:33. And then I'll do a couple of little examples with the chain rule, and then probably set us up for the inverse function theorem, but maybe not prove it, because I think the proof is actually longer than this one. Okay. So I will leave this up in its totality. Hopefully you can read it in this small size in case you want to look over it. If you have any questions, throw them in the chat. I'll answer them as I go. But otherwise, like I said, 10 minutes, and I'll meet you back here at 10:33. Okay. All right, so we're gonna move on. And again, if you're still struggling with the proof of the chain rule, it's not the end of the world. Again, there's a sense in which it's a nice thing to know, and you should have seen it at one point in your life. That sort of thing, though, is not going to be, it's really not going to come up again in any of our studies. It's just, again, like to understand that there is this tricky technical aspect that we need to make sure that we've taken care of. And it's precisely because we want to be able to use change of variables. Your test mark. So one of the 3 questions is marked. The other TA is going to start tomorrow. And then I don't know about the third, but hopefully by the end of the week. And if not by the end of the week, early next week. Yeah. Usually we give the TAs about a week or so, right? Sometimes they take a little bit longer, and we're sympathetic to that because they're students as well, right? But usually it's about a week, yeah. Though sometimes I have to get on their cases and give them hell. Okay, so I guess we should do a quick example of the chain rule. And so the great thing, about having all that technical detail in the proof of the chain rule itself is that you don't have to worry about it when it actually comes time to apply the chain rule, right? Well, it depends on what you mean by this. Like, someone can prove a theorem by themselves when they first see it. I mean, first of all, there are people who are just phenomenally gifted, right, at mathematics. I suspect that I actually don't know the history of the chain rule proof. What I do suspect is that the first people, when they would have done it, would have done the bad proof. And then somebody probably pointed out that, oh, hey, you're actually not allowed to do that. You've violated something. And, but we can fix it. We can patch that hole. So that's kind of what I suspect the history of that proof would have been. And there's stuff like that all the time. Like, there's a very famous, for example, result in my, in the field that I was doing my PhD research in, where a very famous mathematician said, by continuity, this thing is true. And it absolutely was not true, because you didn't know that function was continuous, and he had to fix his proof, and he fixed it 8 years later or something like that. These sorts of things absolutely happen, where there's just, you can see here, right? The problem is very subtle. And so if I had to guess, I would imagine someone did the bad proof first, and then they fixed it later. But notably, Leibniz and Newton, and in, for example, the Bernoullis and all those people, L'Hopital, the people who really are part of the foundational finding of a lot of the first calculus results, especially differential calculus, really did a really bad job their first go through. They weren't rigorous at all. So Newton, notably, I don't believe used epsilon delta, right? And neither did Leibniz. They kind of had this notion of what a limit should be and what it should do, and were fairly sloppy with it. And then we came back later and made sure that we could do it rigorously and really clean it up. So this is what I'm saying. especially the chain rule here, probably bad proved first and then was fixed later. So yeah, this is the sort of thing I would say, don't worry about it. But that being said, there are definitely people in the world who are actually really, really good at noticing this. In the case of Newton and Leibniz, we wouldn't blame them just because the notion of rigor was, I think, much weaker in their time than it is today, right? Nowadays, we are really about pure, like extreme rigor, not just being able to roughly argue it, but being able to ensure that you're 100% precise. And so today's level of rigor is different, right? But yeah, I don't think this was probably proved correctly on its first try. But calculus especially is kind of replete with examples of these things, right? So I'm going to do a relatively simple example. I'm going to just say find the derivative of x squared plus x plus 1 to the 2021. Okay. And so the reason I really like this one, this doesn't necessarily apply anymore, but, back in the day, people would be like, oh yeah, well, why do I need to learn all of these tools? I could just plug things into the computer. And it used to be, computer algebra systems have gotten a little bit smarter, but when I was an undergrad, if you tried to get a computer to do this, Maple, Wolfram Alpha, whatever the case might be, it would expand this thing out for you, right? It didn't use the chain rule. It would expand out x squared plus x plus 1 to the power of 2021 as this disgusting, huge polynomial. And then it would just apply the power rule, right? And you could absolutely do that, and that would be fine. And of course, the computer doesn't care, because for the computer, that's a relatively straightforward thing. But you can imagine for you and me, we do not want to expand out this polynomial and then differentiate, right? So that's kind of like why I like this example. But I don't, it's not a terribly difficult example. So I'm going to let f be, no, actually, I'm going to let f be x to the 2021. And g of x be the thing inside, x squared plus x plus 1. So that f composed g is the function that we're trying to differentiate, right? X squared plus x plus 1 to the 20. Oh, I've run out of space. So we're going to zoom out a little bit to the 2021 like that, right? And now both of these functions are everywhere differentiable. And we can easily compute their derivatives. So by the power rule, this is this. And g prime is 2x plus 1. So by the chain rule, we're going to get 2021, x squared plus x plus 1, 2020, 2x plus 1, like that, and we're done. Okay. And of course, when you're doing it, you don't need to break it into these steps. Like if you're comfortable, especially if you've done, calculus in high school, I'm certain that you've used the chain rule before, and many people can just do this in their head, which is totally fine. So you don't need to break things down into F and G's. If you don't want to, you can just go straight to the answer. But if you need to do that, that's fine. I think it's worth pointing out very, very quickly, if you have multiple functions, right? Because there's no guarantee that any function that you get will just simply be a composition of two functions. It could actually be a composition of more things, right? So if I ask you, for example, to differentiate F compose G compose H, right? You do your normal, almost like sort of induction thing where you treat G compose H as a single function, right? So you might do something like F prime of G of H of X times the derivative of G compose H of X, right? So you just kind of recursively and inductively work out what the answer should be times G prime H of X times H prime of X, like that, right? And you can imagine you can do this with as many functions as you like. Now, for me, this always just reminds me of like Matryoshka dolls. You guys know what Matryoshka dolls are? Right? Exactly. So yeah, look them up. How do we spell Matryoshka dolls? Matryoshka. Yeah, they're exactly the Russian nesting dolls, right? So to me, these are the nesting dolls, right? So you've got F compose G compose H, right? They're nested inside of each other. And if you look at what their derivative is, it's like, okay, I've got F prime, and then I've got the two dolls still inside of it. So I'm going to pull them out. And then I've got G prime, and it's still got a doll inside of it. So I pull it out, and then I've got an H prime, right? So I've always kind of like viewed it like this, which for me makes it very easy to remember that I just keep pulling the dolls out. And every time I pull a doll out, it picks up a derivative, right? So that's for me when I have these long sorts of compositions, that's exactly how I internalize how the derivative works, right? It's precisely by the Matryoshka dolls. Now, if that doesn't work for you, you do what you want. But there are absolutely could be cases where you have long convoluted sequences of functions that you need to be able to differentiate using the chain rule, right? I guess the proof of this needs more f of x. Well, so again, right, the whole point of the technicality of introducing the capital F in the proof of the chain rule is that once we know the chain rule is true, we don't need to worry about the technicalities anymore, right? In this previous exercise that we just did, we know that our functions are differentiable at their points. They're actually differentiable everywhere. So the technicality doesn't come in because the technicality was in the proof, and so it got buried there, right? So we don't need to worry about that anymore. We can just go ahead and we can use the tool. The technicality got buried in the proof itself, and that's a good place. That's where we want it, right? Because you prove a thing once, and then you forget about it. So if we can bury the technicality there, we don't have to use it every time we actually invoke the chain rule, right? So that's why we want to bury our technicalities in the proofs. Okay, a nice little exercise for you is to figure out how would you actually write down. So let's say I gave you an n-fold composition of functions, right? So it's not just to figure out the derivative, but how would you actually even write it down? So if I gave you something like, suppose f1 through fn are all differentiable. Let's just say they're differentiable everywhere, so we don't have to worry about, f2 is differentiable at f1 of c, f3 is differentiable at f2, compose f1 of c. Let's not worry about that. Let's just say these functions are everywhere differentiable. What I want you to do is see if you can figure out a good way of writing down what this derivative should be, right? So we know that it follows this pattern from above, very similar to the Matryoshka dolls where you keep pulling them out, right? But how do you write this down for an arbitrary n, right? Like how do you actually write down that expression for an arbitrary collection of functions? And while you're at it, you could do the same sort of thing with the product rule, right? Because we know if you have a product of 3 functions, what the product rule becomes, and how would you write that down in general, okay? So I think that this is an interesting little exercise in just playing around with notation. See if you can figure out a way of writing this down, ideally without using ellipses, right? Without doing ... guess what the pattern is. See if you can actually write it out. You'll probably want to use pi notation, right? Like the big product, right? So instead of sigma being a sum, you'll probably want to use the big pi notation as a product in order to figure out what it should look like. Okay, so see if you can invent some notation like that. Okay, I guess, I don't know if I want to start the inverse function theorem, but let's see. I might state it, but I don't want to start the proof because the proof is going to take, the proof will probably take like 20, 30 minutes. So maybe let me just set it up and then I'll state it for you and then you can think about it. Even better, you can try and prove it, right? I think that would be great. So the first thing we're going to need is this lemma. And we're going to prove this lemma later. So I'm going to bring it up. This argument is not circular because we don't need anything that we're going to do in this section in order to prove this lemma. But this is the right time to introduce this theorem. the inverse function theorem, but not the right time to introduce this lemma. So, you know, as a book writer, you're kind of like conflicted as to where to put this lemma. Anyway, whatever. It goes like this. So suppose f is differentiable on an interval AB, and f prime of x is greater than 0 for all x in AB, then f is strictly increasing on AB. Right? And I think many of you not only could guess that this is true, but you've probably seen this result before. You're proving something similar to this in assignment 5, not exactly the same, just similar. But again, this is probably sort of an intuitive thing. We know that f prime is supposed to denote your instantaneous rate of change. So if your instantaneous rate of change is always positive, then you should be always increasing, right? If your rate of change is positive on this entire interval, what else could you be doing other than getting bigger, right? And you're always getting strictly bigger. So again, we're going to prove this. We need to first learn the mean value theorem in order to be able to do this. So that's still a week or two away, but I do want to introduce this now. So I'm going to leave this lemma here. So we're going to prove this later, but I think it is intuitive enough that introducing this at this point without proof is okay. All right. So that's great. And also, what are some other things that we now immediately get for free? Well, we know that increasing functions, for example, are injective, right? That's nice. So we get stuff like that. All right. So this is, I'm going to state this, but we're not going to do the proof of this until Thursday. This is the inverse function theorem. There is a very real sense, okay, where this theorem, the inverse function theorem, is one of the most important theorems in mathematics, period. It's not going to be obvious by the version that we're going to state and prove in this class, but if you go and you take higher mathematics, there is a more general version of the inverse function theorem that is basically, it is this theorem, it's just, you know, done in general. And that version of that theorem is one of the most important theorems in mathematics. This is a special case where we're only going to deal with functions that map the real numbers to the real numbers. But as you start looking at, you know, maps from like Rn to Rn instead of just R to R, it becomes super important. It's crazy how important it is and how often it comes up. Okay, you can prove some very big, very important theorems from this. So this theorem statement goes like this. Did I define C1 for you? Right, that the function and its derivative is continuous? Okay. So suppose that f mapping R, we're just going to state it as R to R, is a C1 function, right? So it's differentiable. I'm just going to remind you in case you've forgotten, differentiable and f prime is continuous. Okay, so f maps R to R is a C1 function, and f prime of P is greater than 0. There exists an open interval U containing C and V. I guess I should say there exist open intervals. Let me say it like that. There exist open intervals U containing C and V containing f of C such that I'm going to call it f hat, which is the map from U to V, which maps C to, X, is bijective and f hat inverse is C1 with f hat inverse prime of y equals 1 over f hat prime f hat inverse of y. Okay, so there's a lot to take in there. The thing that I want to make sure that we're all clear about, though, is what is f hat. So what we're saying is that, look, you f hat is just, it's still f, right? It's exactly the function f, except I've restricted it to the interval u, right? So f is a function from r to r, and it might or might not be bijective and invertible. We have no idea. But what we're saying is, if there's a point where the derivative of f, actually, instead of changing derivative of f is greater than 0, let's just say is not equal to 0. If there's a point where the derivative of f is not 0, then by restricting f to a small enough interval, I can be guaranteed that it is bijective. Okay, so I can be guaranteed that it's bijective. Not only that, that's not the big deal. That part's easy to prove. Not only is f bijective, well, since it's bijective, we know it has an inverse. That inverse is also C1, right? That's a huge deal. We know that this function has a set theoretic inverse, but why should it be differentiable? Why should the inverse of a differentiable function be differentiable? Generally, that's not true. But the inverse function theorem guarantees that the inverse function will be differentiable, its derivative will be continuous, and it explicitly gives us a formula for the derivative of the inverse function. Okay, so this is a big theorem. You can imagine it's telling you a lot. All you have to do is tell me that your function has a non-zero derivative at a point, and I can be guaranteed that it is locally bijective and its inverse is C1, and I can tell you exactly what the derivative of the inverse is, right? That is crazy. That is powerful. The test question, it's similar, right? It didn't, like, test question 3 didn't involve any differentiability, but in fact, we are going to use question 3 from the test in the proof of this, right? So I'm actually not going to prove it because I've already posted the solutions, but I'm going to say, you know, by question 3 of the test, we've already proven that the inverse function is continuous, for example, right? And so we don't need to do that. And I can go straight to proving that it's differentiable. But you're right, it does have a lot in common with that question from test, with question 3 from test 2. Okay, so does everyone, what is P? It's just some point. Yeah, maybe I should include that in. And f prime of P is not 0 for some P in R. Right? It just says, you give me a point where the derivative is not 0 and the rest of the theorem comes out. It doesn't matter. If you want to call it, if you want to put an X here instead, you totally can. I'm just trying to be consistent with this idea that sometimes we think of the inputs for the inverse function being Y's. It doesn't matter though, right? You kind of call them what you want. Or another way you could do it is if Y is equal to F hat of X, then you could write this instead as F hat inverse prime of Y is equal to 1 over F hat prime of X. So that might be a better way of thinking about it if you prefer. This is nice because it kind of really nicely illustrates what the relationship between X and Y is. But in practice, you tend to use this formula when you're invoking the inverse function theorem. But the thing that I've put in a rectangle can be nicer because, again, it kind of clearly illustrates to you what the relationship between these two things is. And again, there's a sense in which this isn't surprising. If you think about what f prime is, it's the slope of the tangent line. When you take the inverse, you reflect about the line y equals x, right? So you take your function, you reflect it in the line y equals x, and you could say what should happen to the slope of the tangent line when you reflect about the line y equals x. Well, you'll just take 1 over it, right? You'll take a reciprocal of it. And this can actually, kind of tell you why you don't want f prime to be 0, because if f prime is 0, it means your tangent is horizontal. when you reflected about the line y equals x, it would then become vertical, right? And we know that vertical tangent lines are not allowed. But if you give me any other, tangent, when you flip it or reflected about the line y equals x, you pick up the reciprocal of the slope, right? Again, you might need to convince yourself that that's true, but that's the geometric intuition behind why this formula should be right, right? Reflecting a line about y equals x, the slope of the reflected line will be 1 over the slope of the original line. Did I use a C somewhere? There's C1, but C1 means differentiable and the derivative is continuous. So did I use it? Oh, containing P, sorry. And containing f of P. Yeah, thank you. Okay. And I mean, like, again, we could even kind of like draw a picture here. I don't know how good my picture is going to be. But the idea is you've got some sort of function, the derivative here is positive. So my function is actually, let me draw something which is not invertible. But it is invertible in some neighborhood, right? So the derivative here is definitely positive. So there's some neighborhood U on which the function is actually bijective, V, and then when you reflect about the line y equals x, I don't know, what is that going to look like? That's going to look something like, what is this going to look like? So it's going to look like, something like this. And then the tangent lines will just end up being kind of reciprocals of one another. So at this point, well, I mean, unfortunately, I've drawn them as kind of both having slope 1. So we don't really see the reciprocals come out. Maybe I need to take my point a little bit higher. Let's maybe draw the point here, right? So the tangent line is like this. And then here, the tangent line is much steeper. Does that make sense? So that's basically the geometry behind what the picture is doing. I'll redraw this. I'll try and draw it better when we come back. But yeah, that's the idea. So your derivative is increasing. You can take a slice of the function so that it is actually a bijective map. And then when you reflect the graph about the line y equals x, the tangent line slope should change to 1 over m instead of m. Does that make sense? Do you kind of see what the picture there is? Maybe. All right, well, you can think about it. Anyway, that's going to take care of us for the day. So it's 11 o'clock now. Yeah, think about this one a little bit more. See where that takes you. And even better is if you can try and prove this on your own. The proof is not terrible, but again, it's kind of technical, right? Is it even technical? It's just notationally a little bit messy. I don't even think it's technical. It's just notationally a bit messy. Okay, so you can try it on your own, see how far you can get. The only thing you really have to do is prove that the inverse is differentiable. Most of the other stuff will come very, very quickly, but see how far in that you can get. But either way, I'm going to take it up on Thursday and we can talk about it then. Okay, so if there are any last minute questions, please don't hesitate to ask them. I will hang around for a little bit and answer. Otherwise, you're free to take off and I will see you on Thursday. Thank you. Sure. Yeah. Sophia Maria, what's up?
I'll say it because thing 3.1-19 part B. I'm just